Well, my name is Kate Long, and I work for the California Governor's Office of Emergency Services, where I'm the Earthquake Program Officer. And but I work my duty station is actually at Caltech with the USGS earthquake program there. So I am a fuzzy in a house of techies. And as an emergency manager and as a fuzzy, I love a good catastrophic scenario. I got to get out more. But I am very excited about this HayWired session because it is an early preview, and I think maybe the first preview of the next scenario from the SAFER group, the Science Application for Risk Reduction at USGS. And our panelists today both worked on this scenario and on a number of other SAFER-led scenarios, which are so important to emergency managers. Keith Porter, who is a research professor of structural engineering and engineering mechanics at the University of Colorado at Boulder, and Dr. Charles Scawthorne from the UC Berkeley, and PEER, the Pacific Engineering Research Institute. But before we go on and hear from our panelists, I did want to introduce one other person, and that is Ken Hudnut. If you'd stand up, Ken. Ken is the brand new science advisor for the SAFER project, succeeding Lucy Jones, who has retired. And there are a number of other people who are working, a huge number of other people who are working on the HayWired scenario, because one of the things that the SAFER scenarios do is start from the earth science to the damage, to the economic impacts, to the social and long-term impacts, and really do the kind of robust scenario creation that makes emergency managers very happy. So HayWired is really robust, and I was asked to moderate this session because we, the emergency managers, are the customers for a lot of what SAFER does, and we're tremendously appreciative of the USGS for reaching across and working with this huge range of stakeholders, emergency managers, lifeline providers, economists, everybody, to try to make their science useful to us on the implementation end. And the reason they do a lot of scenarios is because they started out the SAFER project by saying, what do you need? And we said scenarios, because we use them for planning, we use them for exercising, and having a scenario that's based on a probable catastrophic event and probable results and secondary results is hugely important to us. And this is an event that we need to be ready for. And so that's really great. We will use it extensively, and we're already using it. Actually, it was it's an event on the HayWierd Fault, which is arguably the most urbanized fault in the country, and it's 7.0. And we in the emergency management community have just done some catastrophic planning for the Bay Area, updated a catastrophic plan, which our first iteration of the plan just used as a scenario a repeat of the 1906 San Francisco earthquake. But in California, you've seen the picture of the faults. You know that we're 66% down from 70. It's not that we're getting better. The rest of the country is we're knowing more about the rest of the country. But we will use it. We used it in preparing our plan, and we will continue to use it because our next iteration of the plan was on a little faster time track, and we're ready to release this particular iteration of the catastrophic plan. But we will use HayWired in our exercises, and from the results of that, the next iteration of the catastrophic plan will be better and better. So I want to just hear from our panelists, as one of the most excited audience members here, about what's new, what are the headlines. We can't hear everything, but this is going to give us a preview of some of the biggest problems that the HayWired scenario helped us uncover, including infrastructure interdependencies and fire following. So, Keith?
Thanks, Kate. All righty. So I'm going to tell you a few of the lessons that I think you may be interested in from the HayWired scenario. As Kate showed, this was a large collaborative project. There are dozens and dozens of people to thank, but I want to particularly thank Jamie Jones, who produced most of the maps you're going to see here. So the SAFER project has as its mission to innovate the application of hazard science for safety, security, and economic well-being of the nation, and it has done that so far. There's many projects that have come out of SAFER. Three of the ones that Dr. Scawthorne and I have been involved in are these three scenarios. The shakeout scenario, which you might think of as the big one, the arc storm scenario, which if you haven't heard about it, is an even bigger one. It's a severe winter storm that strikes California every few centuries. And it's the last one is outside of living memory, but it is a much bigger event because it affects the entire state simultaneously. And yet another one, the SAFER tsunami scenario, which nonetheless it's much smaller, but it affects people along the coast pretty severely. So what is new? Why would we want to create yet another disaster planning scenario that's an earthquake? This particular one is a magnitude 7 Hayward Fault earthquake. And what we're doing here that's new, that we didn't do in Shakeout and the others is, well, for one thing, we're including the entire earthquake sequence, including 16 magnitude 5 and larger aftershocks. Down here, you can see the aftershock sequence, one simulation among many. Some new and unusual engineering features of HayWired. I'm an engineer, so I'm going to tell you about the engineering features. All the results you see here are still officially draft, so they could change before publication. First, we're treating the entire earthquake sequence. We are examining the difference between physics-based, that is 3D modeling, maps versus shake maps that are created using ground motion prediction equations. They make a big difference. On the left, you're seeing a map that is the median of shaking, and on the right, you're seeing the simulation of shaking that 13 authors at the USGS created about 6 years ago that we're using. We did a little study on the area affected by building collapse. Amazingly, we really don't know when a building collapses what fraction of the building actually sort of comes down. So this was an early study of the fraction of the building area that actually comes down by studying photographs of all buildings in California earthquakes of the last 50 years at this NEC database where the word collapse or collapse was known to happen. We studied the photographs of every one of those buildings and created this little pie chart here. We created a new urban search and rescue model that considers both the number of people who are trapped in collapsed buildings and need extrication by fire department and other search and rescue people, but also the number of people who would be trapped in elevators that are stalled between earthquakes. And as near as we can tell, the number of people trapped in collapsed buildings is going to be small. If the earthquake happened in the middle of the day or late in the afternoon, would be relatively small compared with the number of people trapped in elevators. So this is a big deal, the fact that large numbers of people will be trapped in elevators. We looked at earthquake early warning and in combination with drop, cover, and hold on. And imagining that all of the latency issues that Doug Given talked about a little earlier on today could be addressed and taken care of, and imagining that 100% of people had earthquake early warning on their cell phones or otherwise, instead of the 90% that Doug told us about. We estimate that earthquake early warning could prevent up to 1,500 injuries by giving people a little bit of extra time to drop, cover, and hold on. We did this by a public study of how long it actually takes people to drop, cover, and hold on. So that's kind of interesting novelty. We're dealing a lot with lifeline interaction in the HayWired scenario that we haven't done so much in previous scenarios. But now I want to tell you in depth about one of the more interesting aspects of the scenario. We created a new model of water supply damage. Now, obviously, earthquakes damage water supply pipes, and you're going to see how that's important a little bit later on when Dr. Scawthorne tells you about fire following earthquake. But earthquakes shake the ground, they cause ground shaking, they cause ground failure in the form of liquefaction, landslide, lateral spreading. We saw this in many, many earthquakes in the Bay Area in 1989. There were 865 water and sewer breaks, and that was not a Bay Area earthquake. So a Bay Area earthquake is going to see many, many more pipeline breaks. What happens when all those pipeline breaks occur? Now, this is not new engineering to estimate the damage to water supply pipelines. There have been many studies over the past several decades that have created models of water supply damage. I'm listing here some of the leading ones. But we intended to add a little bit to that literature. We are employing physics-based ground motion models. We are treating the entire earthquake sequence, which not many of those past studies have gotten around to doing. We are quantifying and propagating leading uncertainties. We are dealing with service restoration. A lot of models deal with the initial damage and not so much with the service restoration. Service restoration in this model considers lifeline interaction. It considers the availability of repair crews, mutual aid, productivity over time, fuel, and other consumables that a water utility will need to do the repairs. It quantifies losses in terms of service days lost, and it quantifies the benefit of resilience options. And we've also managed to trick HAZUS into treating lifeline interaction and other features in this detailed model that HAZUS doesn't yet do. And my advancer is not working. And there's no option up here for there we go. Okay, good. Okay, so the first step in estimating the damage to pipelines is to know where they are. You have to get a system map of where all the pipelines are and what they're all made of. This map here shows the East Bay Municipal Utility District's water supply network. The next thing you have to do is you have to estimate the damage to each segment of pipe as a function of ground shaking, as a function of landsliding, liquefaction, co-seismic slip, and after slip. So all these things are handled by the model. The next thing you do is you estimate the initial post-earthquake level of service as a function of break rates per number of breaks per kilometer. On the vertical axis there, you're seeing 100% at the top service, and at the bottom, no water service, and left to right is very low levels of damage to pipes, and at the right is very high levels of damage to pipe. We then, in our model of restoration, we assume that the most effective repairs are performed first, and that the repair rate, the rate at which pipes breaks and leaks are repaired, depends on repairs per crew hour under normal circumstances, the fraction of the day that crews work, because we imagine that they'll work 12 hours or longer days after a big earthquake, the number of repair crews that are available, and that number changes over time. The importance of fuel, electricity, telecommunications, etc., to actually carrying out those repairs, and the availability of each of those resources for performing repairs. And we did two case studies. One was of the East Bay Municipal Utility District. Here is their water supply pipeline network showing the number of kilometers of pipe and the number of services east and west of the Oakland Hills, which they consider to be an important boundary. Here's the estimate of one possible outcome of main shock damage. This is a heat map, and the brighter the color there, the more dense the damage. And of course, as one would expect, you get more damage near the fault and on poor soil. We estimated damage in each of these 16 aftershocks. This is one of the larger ones. Initially, and then we calculate the initial level of service right after the earthquake. East of the fault, where the system and the pipe is generally newer, there's about 85% service. That is to say, 85% of customers are getting adequate water out of the tap. But west of the fault, where most of the customers are, there's about 10-15% of customers are actually getting service. So 85% of people west of the Oakland Hills are without water very shortly after this earthquake. Crew availability changes over time. This is a map of how they, on the horizontal axis, you're seeing time. On the vertical axis, the number of crews available. There's an initial period of reconnaissance, then mutual aid starts to flood in, and then the mutual aid has to be released, and the East Bay Mud crews have to handle all of their repairs. We track how electricity is restored over time because that affects how productive the repair crews can be. We track how cellular communication recovers over time because those repair crews obviously have to be able to communicate with headquarters to know where to go and where the breaks are and so on. We examined a couple of resilience options. One is to have to deal with the problem of fuel shortage. So once the power goes out, there's going to be limited ability to get fuel out of gas stations and whatnot. So one option for a utility is to stockpile their own fuel with their own pumps to get the fuel out of those tanks. Another option is to replace all of the very old cast iron and asbestos cement and other brittle pipe in the system. That's a huge challenge for East Bay Mud. They've got 2,400 miles of brittle pipe that would cost $5 billion to replace. This is not something that happens in a space of years. We then track repairs over time, considering all these things that I've just shown you, and more interesting is the restoration of service. Now, on the vertical axis, you're seeing the number of customers who have water coming out of the tap at various points in time, which are on the left, which are on the horizontal axis, and this is a log scale, so, oops, that was my fault. There we go. 10 days, 100 days, 1,000 days. The lowest curve here is what happens under as-is conditions with the pipeline network they've got. The upper curve is what happens if all that brittle pipe were replaced before the earthquake happens. And we can measure the area above this curve. This is all this shaded area is the customers who have lost water. So you can measure the loss of resilience in terms of the area above this curve. Let's see. So here's some summary statistics of three conditions. Under as-is conditions, the average customer is without water for 40 days, but some customers are without water for 6 months. If East Bay Mud were to institute a fuel plan, they could save a day in average reduction in service loss. But that day, on average, over so many customers is worth $150 million just from putting a few tanks in their service yards. If they were able to replace all the fragile pipe, they would still only cut the average loss of water by half, but that over all those customers, that saves $6 billion, rough estimate, of value. So there is a lot of value in replacing fragile pipe quickly. So in summary, water supply impairment for East Bay Municipal Utility District could last months. If they replaced all their old brittle pipe, they could cut their loss of service by 50%. It would cost on the order of $5 billion and save on the order of $6 billion, not counting the reduction in fire damage. We performed similar analyses for San Jose Water Company. Jim Wilbrink, its emergency manager, liked this scenario because it gave him a great scenario to start planning and training against. Now, with that, with damage to water supply as a backdrop, I'd like to ask Charlie to come up and talk about fire following earth.
He'll be back. Thank you very much, Keith, and a pleasure to be here this afternoon. And Keith, you skipped?
Sorry.
There we go. Do you want, actually, sorry, can I go back here? Do you want to say anything about that slide?
Oh, yeah, sure. Because Kate asked, because the organizers asked us to talk about what's new, what's next, and what our role is. This is just a summary. Through SAFER, we hope to empower lifeline operators to quantify their resilience benefits of renewing infrastructure and planning for a better response. So go ahead.
Thank you very much. And let me begin, first of all, just simply by saying I'm rather humbled to be up here because you saw the team that Kate listed of all the people involved in this SAFER study, and Keith and I are only two of these people, and we're standing on the shoulders of a lot of other people in doing this work. So I'm going to speak briefly about this scenario and the issue of fire following earthquake and the lessons for emergency managers. Let me begin simply by a caveat that this work has not yet been released by the USGS, and so the final results will be released at some point in the future. Moving ahead now, I'm not going to spend much time discussing the fire following earthquake problem. We all know 1906. This is a picture of 1989, 1994 Northridge. This is a picture from downtown Tokyo in the 2011 Tohoku earthquake, which had over 300 fires following that earthquake across a large part of Japan, of course. And under non-earthquake conditions, fire departments are extremely challenged in selected fires. This is the 1991 First Interstate Bank building in Los Angeles, tallest building in California at the time, and it required only 4 floors burnt out, although everything below that, the building was damaged for a year due to water damage below the fire, as well as the fire damage on 4 floors and the smoke damage above, and required the resources of about 1/3 of the Los Angeles City Fire Department to combat it under non-earthquake conditions. And there are many other examples of where fire departments are challenged under non-earthquake conditions with one fire. I'm not going to go into a lot of detail of the analysis. There's a large body of work here. These are some of the publications over the last 35 years on how to go about modeling it, the data that goes into the models, and so on and so forth. And some of that is detailed in the previous shakeout study and will be released in this study when it is released. But in summary, it involves several major aspects: the earthquake damage, the multiple simultaneous ignitions, which I'll be talking about, the fire spread, the water supply and response problems, which Keith has talked about, the communications breakdowns, and the competing demands. The fire service is also being asked to do search and rescue, medical, hazmat at the same time as fires. The basic model is shown here. And basically, this is a timeline. This is time. This is the time of the earthquake right here. The earthquake occurs. And each of these bars represents an ignition. The ignition is shown as the first ignition, second, and so on, just numbers. And many of them occur very soon after the earthquake, but other ignitions are delayed by some time. When an ignition occurs, there's a period during which the fire grows. And the growth of the fire is shown by the width of the red bars. And so the fire is growing from a fire that could be suppressed by 1 engine to 2 engines to 3 engines, requires 3 engines to suppress it, and so on. And it has not yet been discovered. Finally, there is a discovery, and this is a key issue that's why 911 is so important and so on. And after earthquake, when it is saturated, there will be delayed discovery of fires and delayed reporting because it requires a report for the fire department to get there. In any event, the fire department does respond. And when the engine gets there, it suppresses this fire and turns the red bar to a blue bar, showing that it's been suppressed. And that fire department then picks up and goes on to another fire engine, goes on and responds to another one. And eventually they all converge, they suppress many of these, and they converge on one or more large fires, and the issue is, do these grow into conflagrations or not? And that's what the modeling does, and as I said, is documented in a number of reports. So it's a stochastic process. There's a lot of uncertainty involved in it. It begins with the ignition occurrence and fire spread given the performance of the gas and power systems. Also the water supply, given the damage to the distribution system, which Keith spoke about. The fire reporting, given the saturation of the plain old telephone system, the cellular 911 systems. The fire department decision making, their radio chatter, their self-dispatching companies, the overwhelmed EOC, and so on, and other demands, as I talked about that. In other words, it's a rather complex process. Having said that, now coming to the HayWired scenario, we started with the input data, which is the shaking intensities, the building exposure throughout the Bay Area, and the fire service assets, or basically fire engines and firefighters who are available. Now, so we have all this data, and these sort of beehive cells around each fire engine were generated to approximate the fire response area of each fire engine. So these are where that fire engine would respond to fires within that area, and so on and so forth. Naturally, the denser the population, the denser the concentration of fire engines, fire departments, fire engines. So the actual input data is shown here. We looked at portions of 9 Bay Area counties, almost 7 million people, about 6 billion total building square foot area, and over $1 trillion if we just use an average of $200 a square foot of exposed building value. To model the ignitions, there are 2 models that are currently available out there. One developed for, sorry, I'm pushing the wrong button here. One developed for HAZUS by myself, and that's used in HAZUS, and the other one developed by Professor Rachel Davidson at the University of Delaware, and is under MCO work. It's also published in the Journal of Risk Analysis. And basically, they largely use the same 2 data sets of post-earthquake ignitions in the United States in the 20th century. If we compare these 2, the red is Davidson's model, and the black is the model from the HAZUS model. And this shows with increasing intensity of, and the dotted lines are uncertainty bounds on it. This shows with increasing intensity the ignition rate on a normalized basis on the general, for all building types, and then this one shows just for residential. So you can see that the 2 models, which began with the same data sets, generally agree reasonably well, if not very well in certain cases, for residential, for example. Keith has gone into water supply damage. The model looked at took water supply damage and translated it, not only the normal distribution, but also alternative water supplies, ponds, lakes, swimming pools, access to the largest body of water on Earth, that is the Pacific Ocean and the Bay, and translated this into what's called a water supply factor for each of the response areas. And the bluer, the area would mean that water is more generally likely to be available in that area for suppressing fires, and the redder the area, the less likely water is to be available from any source for suppressing fires in that area. So I think, you get the picture here. So given that, another issue is the ability of fire departments when they're missing when they have dry hydrants in these areas, when the damage that Keith talked about results in dry hydrants. So how are they going to move water from the bay or from a lake or a swimming pool to where the fire is? In many cases, they may have to move it a mile or more. And most people in the audience have not considered that, unless you're in the fire service, and it is extremely non-trivial. As a matter of fact, it's very challenging, and actually, in many cases, exceeds the ability of fire departments to do that. To investigate that, a couple of years ago, and this is part of the model, the Pacific Earthquake Engineering Research Center examined water supply reliability and did surveys of both the water departments and the fire departments. These are survey monkey types of things. We got responses by agencies representing over 1/3 of urbanized California. I won't go into the details. The key findings were that the water departments and the fire departments both say they saw earthquakes as a very important issue. However, they infrequently communicate. The fire agencies assume the water will not be available at hydrants, but don't ask. The water agencies know it will not be available, but don't tell. And furthermore, if you speak frankly to most of water agencies, they see provision of potable water as a higher priority than water for firefighting. And the very difficult task of moving water from these sources to the fire service is in many cases not well thought out, not adequately equipped, and not regularly drilled. So the inescapable conclusion is that in selected areas there will be no water after an earthquake. Given those ignitions that I'll show you in a moment, there's also the issue of mutual aid, about fire agencies responding from outside. For example, the East Bay Hills fire of 1991, I was there at the time. I was in the fire at the time with the Oakland Fire Department, and it was very impressive. The California Fire Service in general can mount 100 strike teams constituting 500 fire engines and move them to a site of a fire within a couple of hours. It is extremely impressive, the ability we have in this state. But after this event, It will be very difficult to do that in the time that is required to suppress these fires. Within a day or two, they'll arrive. But there's a couple of key choke points, and those choke points are shown here. This photograph, by the way, is several hundred fire engines lined up on Highway 24 in the 1991 fire. I think I missed a slide here, but there was a slide that showed the ignition, the patterns, density of ignitions, but I think it's somehow, anyway, I'm not, you saw the algorithms that are used to generate the ignitions. In any event, taking into account the damage to the water systems, the ignitions, the density of building construction, the fire department resources, and so on, the pattern of final burnt areas are shown here for the Bay Area. And these show structural fire losses, for example, where red represents over $1 billion in any one particular fire response area. So the final numbers will be released in the report, but you can see it adds up to quite a bit of money. And Mr. Pomeroy and I think Janelle Maffei from CEA are here, and you don't have to worry, you don't insure any of this. Who insures it? The usual fire insurance companies, State Farm, Allstate, and so on. They're 100% on the hook for this. Okay. Now, some of the things that were not addressed in doing this modeling are petroleum refineries. Just like down here around Long Beach in the Bay Area, there are a concentration of major refineries. 5 of them are shown here. These are very large refineries. These were not included in the model, the fires. This is a fire at the Chevron Richmond refinery in 2012, which again is challenging by itself. So that they were not addressed. Another thing that was not addressed actually was the failures of large gas and liquid fuel transmission pipelines. This is not a highway map of the Bay Area, but rather large liquid and gas major transmission lines coming into the Bay Area. And this is the 2010 San Bruno gas explosion, which was rupture of one of those lines at one location that resulted in 38 houses being destroyed, 8 people being killed, and required the San Mateo, about 92 apparatus from the San Mateo County Fire Department to suppress it. And so on. We'll go into that. Now, lastly, let me just say, by way of validation, this work was presented to a workshop of fire service people, mostly from the Bay Area, although LA County and LA City both attended also, at University of California's Richmond Field Station. It was under the auspices of OES and these other agencies. And not only was there a presentation of the results, and actual numbers confidentially were provided to them at that time. I'll come back to that in a second. But also, there was a large demonstration of how to move water from the few departments in the Bay Area that are really equipped to do that, such as Berkeley, which has a 12-inch emergency water supply system, and San Francisco, and so on. The evaluation of the workshop, the workshop was evaluated by the University of Colorado Natural Hazards Center, and the respondents basically found that they agreed and supported the findings of this workshop. So the fire services bought into these results in a big-time way. So to conclude now, lessons. Large fires increase exponentially with earthquake. These are the lessons for emergency managers and local government. Large fires increase exponentially with earthquake magnitude in a major urban area. So the small to moderate earthquakes we have had in California are in our history, such as Northridge with over 110 ignitions, or San Fernando 71 with 109 ignitions, or Loma Prieta, and so on and so forth, are a guide to the future, but don't linearly extrapolate them. They can be misleading if you just base your extrapolations on smaller events. Gas seismic shutoff valves, which I haven't even spoken to, in selected high-density areas can significantly reduce the problem. This is a work in progress. The citizen emergency response teams that have been trained in Los Angeles, San Francisco, and other cities can also mitigate the problem to some extent, but fire response by trained, well-equipped professional fire service is essential. Damage to buried water pipes will result in loss of water in dry hydrants. That's very clear. For fire departments to have a chance, they need special training and equipment to access alternative water supplies. And this leads to the fact that we need a statewide emergency water supply system, which we don't currently have. What do I mean by that? Well, that's shown in the previous slide, this one here. And this is large diameter hose systems, 5-inch to 12-inch hose systems. A few departments have these, but they need to be much more widely equipped throughout the state on a consistent basis in a unified statewide unified emergency water supply system. And with that, I think I'm done, and thank you.
Okay, so thanks, Charlie. I want to talk to you about the other topic of HayWired that I find very, very interesting, and that's the question of whether new buildings are safe enough. Now, I'm going to talk about what new buildings are supposed to do. They're supposed to be life safe. What resilience do we get out of life safety seismic design? I'm going to talk about how new buildings would do in the big one at an aggregate level. I'm going to look into the question of what the public prefers in terms of the future seismic performance of new buildings, and a question of whether communities have to wait for building professions to change the code to enhance, for those communities to enhance their own resilience. So when we talk about the problem of buildings and earthquakes, structural engineers usually like to focus on the existing building stock. We say that's the real problem. But the fact is that we can have more than one real problem. Existing buildings are a real problem, but we can also look at how the building code might or might not get us into the same situation 50 years from now. We can look at whether the building code bakes in disasters into future earthquakes. So what do we expect then from new buildings, setting aside the issue of existing buildings? Risk in engineered buildings from about 1980 until about 2010 was controlled by essentially this document and some of its successors. This established the load and resistance factor design, which is what structural engineers use to design new buildings, and it controlled the probability of life-threatening damage, the probability that any given beam or column or connection would collapse in design-level shaking, and it controlled that to 4%. Now, that 4% was not deliberately selected. It was simply back-calibrated to previous codes, previous design philosophies, where no one ever said, this is how much risk we want to accept. It was just implicit in these previous design procedures. The authors of this load and resistance factor design standard, they had reservations about immortalizing this 4% figure, and they expressed it in their opening chapter. They said that reliability with respect to wind and earthquake loads appears to be relatively low when compared to that of gravity loads. That is to say, 4% probability is fairly high compared with the probability of life-threatening damage from gravity loads. The profession may well feel challenged, they said, to explain why lower safety levels are appropriate for wind and earthquake hazard vis-a-vis gravity loads, but, they said, this report was not the appropriate forum for what should be a profession-wide debate. They called for a profession-wide debate on acceptable risk. Now, that profession-wide debate has not happened. More recently, the authors of FEMA P695, they recommended in a section entitled Acceptable Probability of Collapse, considering risk implicit in modern buildings, that it is suggested that the probability of collapse due to MCE motion, that's the sort of design level motions, be limited to 10%. Again, they are not deliberately selecting this 10%. They said they found that that was what was implicit in load and resistance factor design for the collapse of modern buildings subjected to design level shaking. Since 2010, as Nico Luco told us, the aim is for buildings to have less than 1% collapse probability per 50 years. And there was literally no discussion about whether that was the appropriate level of risk. It was simply the level of risk that was implicit in prior design procedures. And this map is now how we design our buildings to achieve that less than 1% collapse probability in 50 years. Now, that 1% collapse probability in 50 years gives us a fairly safe building stock. What you're seeing here is a table of threats to human life from a variety of hazards. The leading threat to lives of Americans is heart disease, killing nearly 200 people per 100,000 per year. Firearms kill about 10 per 100,000 per year. New buildings are 1/100th of that risk. So we have pretty good safety from a brand new building. But let's ask the question of whether stronger buildings might be desirable. First of all, are they even practical? More actually might not cost very much. We could design buildings to be 50% stronger for a marginal cost of between 1% and 3% of the initial construction cost, according to 4 independent, highly respected structural engineers named here. That was just their judgment, but there's additional support for their judgment. There was a study for the National Institute of Standards and Technology that looked at the cost to design buildings in Memphis, Tennessee to meet the International Building Code as opposed to the 1999 Southern Building Code. They looked at 7 different buildings, and to increase their strength to meet the IBC would involve making them about 60% stronger, but the marginal cost to do so was estimated for each of these buildings to be between 0 and 1% of their construction costs. So very small additional construction cost to achieve a much greater, much stronger building. Why would that be? Now, that just seems unintuitive to a lot of people. Well, the reason has to do with the cost of the various different parts of a building. 2/3 of the cost of a new building is architectural, mechanical, electrical, and plumbing components. 17% is overhead and profit. 8% is the labor that goes into the structural components. The remaining 8% is the material of the structural parts. Now, most of that is for the parts that hold up gravity, just the gravity columns and the floors that don't have to be stronger when we make stronger buildings. Something on the order of 2% of the construction cost of a new building is for the lateral force resisting system. So making that much stronger just increases that 2%. Here's one more reason why we might think that greater strength might not cost very much. We do it all the time. We make buildings on the west side of San Francisco that are 50% stronger than the buildings on the east side of San Francisco, just because of how the seismic hazard is greater on the west side than on the east side, and nobody notices. We build buildings in downtown Los Angeles that if you design them to be just life safe, you could pick up bodily, put down in San Diego, and they would be twice as strong as they needed to be in San Diego. And similarly, we can say that buildings that are just life safe in San Francisco or Los Angeles would be 50% stronger than they needed to be if you picked them up bodily and moved them to Seattle, twice as strong as they needed to be if you put them down in Sacramento. So we do this all the time and nobody notices. Why might we want stronger buildings, buildings that were 50% stronger than code minimum? Well, here's a little plot of collapse probability versus shaking. This is the same curve that is used in developing the maps of design in the building code. What we're seeing here are 2 lines. This is IE equals 1.0. That's life safety seismic design. That's what we get right now for most of our buildings. This curve here is the collapse probability for a building that is 50% stronger than code minimum. What are the implications of these 2 curves when you look at the big one? Well, collapse is not the only thing that happens to buildings in earthquakes. They can be red tagged, they can be yellow tagged, they can be impaired in some way other than collapse. For every collapse, there are 13 red tags, at least in Loma Prieta and Northridge, and nearly 50 yellow tagged buildings. So 63 impaired buildings per collapse. And the tags are believed to undercount the serious damage. Mary Comario, studying red and yellow tags in 1994 Northridge earthquake, found that moderate damage to single-family homes was undercounted. She saw 58,000 homes yellow or red tagged, but nearly 200,000 where the damage was on the order of $30,000 to $40,000 in 1994 dollars. So that is a lot of money that is mostly uninsured. Any kind of impairment, collapse, red tag, or yellow tag can lead to at least months of downtime. She saw that, Dr. Comario saw that about 40% of homeowners began repairs within a year. For the remainder, it took 2 to 3 years to resolve insurance claim, and repairs were likely to be delayed until insurance funding was available. This includes yellow tagged buildings. So people are dealing with impaired buildings for a long time. What happens when we have a big one? We can take the scenario shake map. This is the shake map from the the shakeout scenario, we can divide that level of shaking by the design level shaking and get a kind of a normalized level of shaking that we can compare with this, with that curve of collapse fragility. And then we can map that, we can call that ratio the demand to design ratio, the level of shaking in the earthquake divided by the design level of shaking. And red here indicates places where the map level of shaking is actually occurring in this is a like 2,500 year shaking that is occurring in an earthquake with roughly a 200-year recurrence interval, because the frequency of the level of shaking is not the same thing as the frequency of the earthquake itself. You can have small areas that are very strongly shaken in fairly common earthquakes. We can then map those colors to the degree of impairment. In this map, you're seeing red is nearly 100% of buildings either collapsed, red tagged, or yellow tagged. The green areas are 50% impairment rate. Here's the impairment rate in the magnitude 7 HayWierd fault earthquake. This is under life safety, This is under life safety seismic design. All this red area are buildings that are neighborhoods where virtually the entire building stock is estimated to be impaired under this model. If we made our buildings 50% stronger, you get this map on the right. So much lower levels of impairment. If you overlay the number of buildings that are in each one of those little pixels, you find that with life safety seismic design, nearly 24% of the 2 million buildings in the San Francisco Bay Area are impaired in some way. If we designed them all to be 50% stronger, we'd have something on the order of 5% impairment rate. Okay, so that's a reason why we might want to design our buildings to be a little bit stronger. I want to examine the question now of whether the public should have a say in whether we should be in the life safety versus resilient design. An engineering ethicist, one of the leading engineering ethicists in the country, wrote a paper, and he circulated it with some of his peers, and they agreed with him. And his finding and theirs was that ASCE's Code of Ethics requires civil engineers to make a reasonable effort to elicit and reflect the preferences of the public, whose lives and livelihoods were at stake. In the past, it's been the building professions, the structural engineers, and other building professions who have established what is acceptable risk. But this engineering ethicist is finding that the public must be consulted according to ASCE's own Code of Ethics. We then carried out a study, a public survey of what the public might actually want. So if you accept that they should have a role in stating, in setting design objectives, what would they say if you asked them what they would want? Well, we did. We asked 800 people in California and the central United States what they would prefer from a new building design to code. And the majority said that they wanted, after the big one, they would want buildings to be either at least habitable and ideally functional. Well, we asked them then, would they be willing to pay for it? And the response was yes. This is what it would cost to make a building habitable or functional after the big one, at least on the order of $3 or more per square foot. And the majority of respondents said that they would be willing to pay what it would cost to achieve the objective that they said that they wanted. There's more evidence to support the notion that they want more and they're willing to pay more. This is a drawing from the city of Moore, Oklahoma, which an earlier speaker alluded to. City of Moore had suffered 3 fatal tornadoes in the past 15 years, and they decided enough was enough. They enhanced their code so that new buildings are designed to be to resist wind speeds that are 50% higher than the code at the time was requiring. Now, 50% higher wind speed is 125% greater strength because force goes with the square of wind speed. They adopted a code that had similarly small marginal costs of construction that will enable their new buildings to resist 85% of the tornadoes that occur in Oklahoma. It's actually higher, something like 93%, and much of the remaining tornadoes, much of the footprint of the remaining tornadoes. Another piece of evidence that the public prefers and is willing to pay for more resilient buildings. Lucy Jones talked to the board of the Building Owners and Managers Association of Greater Los Angeles, and they basically said that they would like to see greater strength mandated in the building code. They did not want to see voluntary code enhancements because that would disadvantage them relative to the owner across the street who didn't pay the additional 1% or whatever. But they did want to see an across-the-board increase in building strength. So there's 3 pieces of evidence that suggest that the public wants and is willing to pay for resilient buildings. Now, it would take a long time for this message to go through the building code development cycle. There are alternatives for a community that doesn't want to wait. A simple option for cities is simply to adopt the International Building Code with the requirement that all buildings be built with what's called an earthquake importance factor of 1.5. And here's some simple language that a city could adopt when they adopt the building code. So, in conclusion, life safety only seismic design seems to lead to excess impairment in the big one. We found that it's practical to build a resilient building stock. We found that the public expects and is willing to pay for a resilient building stock. We found that the public is entitled to a say in establishing code objectives. And there's some evidence to show that cities need not wait for the code to catch up with the public's preferences. Thanks very much.